Educational uses only. Make sure we are in this off. Okay, excellent. So we are ready to start.
For scientists, engineers, and dreamers across universities, startups, and industry. AI factories are rising. Built in America. AI factories are rising. Built in America. For scientists, engineers, and dreamers across universities, startups, and industry.
I think we want to try to reach new heights as a civilization, discovering the nature of the universe.
And now, American innovators are clearing the way for abundance, saving lives, shaping vision into reality, lending us a hand, and delivering the future. We will soon power it all with unlimited clean energy. We will extend humanity's reach to the stars. This is America's next Apollo moment. Together, we take the next great leap. Boldly go where no one has gone before. And here is where it all begins.
Welcome to the stage, NVIDIA founder and CEO, Jensen Huang.
Washington, D.C. Washington, D.C., welcome to GTC. It's hard not to be sentimental and proud of America, I got to tell you that. Was that video amazing? Thank you. NVIDIA's creative team does an amazing job. Welcome to GTC. We have a lot to cover with you today. GTC is where we talk about industry, science, computing, the present, and the future. So I've got a lot to cover with you today. But before I start, I want to thank all of our partners who helped sponsor this great event. You'll see all of them around the show. They're here to meet with you. And really great. We couldn't do what we do without all of our ecosystem partners. This is the Super Bowl of AI, people say. And therefore, every Super Bowl should have an amazing pregame show. What do you guys think about the pregame show and our all-star athletes and all-star cast? Look at these guys. Somehow, I turned out the buffest. What do you guys think? I don't know if I had something to do with that. NVIDIA invented a new computing model for the first time in 60 years, as you saw in the video. A new computing model rarely comes about. It takes an enormous amount of time and set of conditions. We invented this computing model because we wanted to solve problems that general purpose computers, normal computers, could not. We also observed that someday, more people use it, more applications use it, the more problems we can solve. This virtuous cycle is now spinning. What we need to do is drive the cost down tremendously so that
Your job doesn't stop. Neither do we. More than 1 million products, every industry, every day. With easy ordering and fast delivery. Call, click, or just stop by. Grainger, for the ones who get it done.
competitive luxury brand vehicle with this low mileage lease.
About it and come up with a plan and execute it. Every single one of that step requires enormous number of tokens to be generated, which is the reason why we need a new type of system, and I call it an AI factory. It's an AI factory for sure. It's unlike a data center of the past. It's an AI factory because this factory produces one thing. Unlike the data centers of the past that does everything, stores files for all of us, runs all kinds of different applications. You could use a data center like you can use your computer for all kinds of applications. You could use it to play a game one day. You could use it to browse the web. You could use it, to do your accounting. And so that is a computer of the past, a universal general purpose computer. The computer I'm talking about here is a factory. It runs basically one thing. It runs AI, and its purpose is designed to produce tokens that are as valuable as possible, meaning they have to be smart. And you want to produce these tokens at incredible rates, because when you ask an AI for something, you would like it to respond. And notice during peak hours, these AIs are now responding slower and slower because it's got a lot of work to do for a lot of people. And so you wanted to produce valuable tokens at incredible rates, and you wanted to produce it cost effectively. Every single word that I used are consistent with an AI factory, with a car factory, or any factory. It is absolutely a factory. And these factories never existed before. And inside these factories are mountains and mountains of chips. Which brings to today. What happened in the last couple of years? And in fact, what happened this last year? Something fairly profound happened this year, actually. If you look, in the beginning of the year, everybody has some attitude about AI. That attitude is generally, this is going to be big, it's going to be the future, and somehow, a few months ago, it kicked into turbocharge. And the reason for that is several things. The first is that we, in the last couple of years, have figured out how to make AI much, much smarter. Rather than just pre-training basically says, let's take all of the information that humans have ever created, let's give it to the AI to learn from. It's essentially memorization and generalization. It's not unlike going to school back when we were kids. The first stage of learning. Pre-training was never meant, just as preschool was never meant to be the end of education. Pre-training, preschool, was simply teaching you the basic skills of intelligence so that you can understand how to learn everything else. Without vocabulary, without understanding of language and how to communicate, how to think, it's impossible to learn everything else. The next is post-training. Post-training, after pre-training, is teaching you skills. Skills to solve problems, break down problems, reason about it, how to solve math problems, how to code, how to think about these problems step by step. Use first principle reasoning. And then after that is where computation really kicks in. As you know, for many of us, we went to school, and that's, in my case, decades ago. But ever since, I've learned more, thought about more, and the reason for that is because we're constantly grounding ourselves in new knowledge, we're constantly doing research, and we're constantly thinking. Thinking is really what intelligence is all about. And so now we have three fundamental technology skills. We have these three technology, pre-training, which still requires enormous amount of computation. We now have post-training, which uses even more computation. And now thinking puts incredible amounts of computation load on the infrastructure because it's thinking on our behalf for every single human. So the amount of computation necessary for AI to think, inference, is really quite extraordinary. Now, I used to hear people say that inference is easy. NVIDIA should do training. NVIDIA's going to do, they're really good at this, so they're going to do training. That inference was easy. How could thinking be easy? Regurgitating memorized content is easy. Regurgitating the multiplication table is easy. Thinking is hard, which is the reason why these three scales, these three new scaling laws, which is all of it in full steam, has put so much pressure on the amount of computation. Now, another thing has happened. From these three scaling laws, we get smarter models. And these smarter models need more compute. But when you get smarter models, you get more intelligence, people use it. If anything happens, I want to be the first one out. Just kidding. I'm sure it's fine. Probably just lunch. My stomach. Was that me? And so where was I? The smarter your models are, the more people use it. It's now more grounded. It's able to reason. It's able to solve problems it never learned how to solve before because it could do research. Go learn about it, come back, break it down, reason about how to answer your question, how to solve your problem, and go off and solve it. The amount of thinking is making the models more intelligent. The more intelligent it is, the more people use it. The more intelligent it is, the more computation is necessary. But here's what happened. This last year, the AI industry turned a corner, meaning that the AI models are now smart enough. They're worthy to pay for it. NVIDIA pays for every license of Cursor, and we gladly do it. We gladly do it because Cursor is helping a several $100,000 employee software engineer or AI researcher be many, many times more productive. So of course we'd be more than happy to do that. These AI models have become good enough that they are worthy to be paid for. Cursor, 11 Labs, Synthesia, Abridge, Open Evidence, the list goes on. Of course, OpenAI, of course, Claude. These models are now so good that people are paying for it. And because people are paying for it and using more of it, and every time they use more of it, you need more compute, we now have two exponentials. These two exponentials, one is the exponential compute requirement of the three scaling law. And the second exponential, the smarter it is, the more people use it, the more computing it needs. Two exponentials now putting pressure on the world's computational resource. At exactly the time when I told you earlier that Moore's law has largely ended. And so the question is, what do we do? If we have these two exponential demands growing, and if we don't find a way to drive the cost down, then this positive feedback system, this circular feedback system, essentially called a virtuous cycle, essential for almost any industry, essential for any platform industry. It was essential for NVIDIA. We have now reached the virtuous cycle of CUDA. The more applications people create, the more valuable CUDA is. The more valuable CUDA is, the more CUDA computers are purchased. The more CUDA computers are purchased, more developers want to create applications for it. That virtuous cycle for NVIDIA has now been achieved after 30 years. We have achieved that also. 15 years later, we've achieved that for AI. AI has now reached the virtuous cycle. And so the more you use it, because the AI is smart and we pay for it, the more profit is generated, the more compute's put on the grid, the more compute is put into AI factories, the more compute, the AI becomes smarter, more people use it, more applications use it, the more problems we can solve. This virtuous cycle is now spinning. What we need to do is drive the cost down tremendously so that one, the user experience is better. When you prompt the AI, it responds to you much faster. And two, so that we keep this virtuous cycle going by driving its cost down so that it could get smarter, so that more people will use it, so that so on and so forth. That virtuous cycle is now spinning. But how do we do that when Moore's law has really reached this limit? Well, the answer is called co-design. You can't just design chips and hope that things on top of it is going to go faster. The best you could do in designing chips is add, 50% more transistors every couple of years. And if you added more transistors, we can add more transistors, and TSMC's got a lot of transistor, incredible company. We just keep adding more transistors. However, that's all in percentages, not exponentials. We need
Percentages
to
versus
compound
exponentials.
exponentials to keep this virtuous cycle going. We call
Wow.
it extreme co-design. NVIDIA is the only company.
Let's go back to that little part right there.
On the grid, the more compute is put into AI factories, the more compute the AI becomes smarter, the smarter, more people use it, more applications use it, the more problems we can solve. This virtuous cycle is now spinning. What we need to do is drive the cost down tremendously so that one, the user experience is better. When you prompt the AI, it responds to you much faster. And two, so that we keep this virtuous cycle going by driving its cost down so that it could get smarter, so that more people use it, so that so on and so forth. That virtuous cycle is now spinning. But how do we do that when Moore's law has really reached this limit? Well, the answer is called co-design. You can't just design chips and hope that things on top of it is going to go faster. The best you could do in designing chips is add, 50% more transistors every couple of years. And if you added more transistors, we can add more transistors, and TSMC's got a lot of transistor, incredible company. We'll just keep adding more transistors. However, that's all in percentages, not exponentials. We need to compound exponentials to keep this virtual cycle going. We call it extreme co-design. NVIDIA is the only company in the world today that literally starts from a blank sheet of paper and can think about new fundamental architecture, computer architecture, new chips, new systems, new software, new model architecture, and new applications all at the same time. So many of the people in this room are here because you're different parts of that layer, different parts of that stack and working with NVIDIA. We fundamentally re-architect everything from the ground up. And then, because AI is such a large problem, we scale it up. We created a whole computer, a computer for the first time that has scaled up into an entire rack. That's one computer, one GPU. And then we scale it out by inventing a new AI Ethernet technology we call Spectrum-X Ethernet. Everybody will say Ethernet's Ethernet. Ethernet's hardly Ethernet. Ethernet, Spectrum-X Ethernet, is designed for AI performance, and it's the reason why it's so successful. And even that's not big enough. We'll fill this entire room of AI supercomputers and GPUs. That's still not big enough because the number of applications and the number of users for AI is continuing to grow exponentially, and we connect multiple of these data centers together, and we call that scale across. Spectrum XGS, gigascale, Spectrum X gigascale, XGS. By doing so, we do co-design at such an enormous level, such an extreme level, that the performance benefits are shocking. Not 50% better each generation, not 25% better each generation, but much, much more. This is the most extreme co-designed computer we've ever made, and quite frankly, made in modern times. Since the IBM System 360, I don't think a computer has been ground up, reinvented like this ever. This system was incredibly hard to create. I'll show you the benefits in just a second. But essentially what we've done, we created, otherwise, hey Janine, you can come out. You have to meet me like halfway. All right, so this is kind of like Captain America's shield. So NVLink 72, if we were to create one giant chip, one giant GPU, this is what it would look like. This is the level of wafer scale processing we would have to do. It's incredible. All of these chips are now put into one giant rack. Did I do that or did somebody else do that? Into that one giant rack. Sometimes I don't feel like I'm up here by myself. This one giant rack makes all of these chips work together as one. It's actually completely incredible. And I'll show you the benefits of that. The way it looks is this. So, thanks, Judy. I like this. All right, ladies and gentlemen, Janine Paul. I got it. In the future, next I'm just gonna go like 4. It's like when you're at home and you can't reach the remote and you just go like this and somebody brings it to you. That's, yeah, same idea. It never happens to me. I'm just dreaming about it. I'm just saying. Okay, so anyhow, we basically, this is what we created in the past. This is NVLink 8. Now, these models are so gigantic. The way we solve it is we turn this model, this gigantic model, into a whole bunch of experts. It's a little bit like a team. And so these experts are good at certain types of problems. And we collect a whole bunch of experts together. And so this giant multi-trillion-dollar AI model has all these different experts, and we put all these different experts on a GPU. Now, this is NVLink 72. We could put all of the chips into one giant fabric, and every single expert can talk to each other. So the master, the primary expert, could talk to all of the distributed work and all of the necessary context and prompts and bunch of data that we have to, bunch of tokens that we have to send to all of the experts. The experts would, whichever one of the experts are selected to solve the answer, would then go off and try to respond, and then it would go off and do that layer after layer after layer. Sometimes 8, sometimes 16, and sometimes these experts, sometimes 64, sometimes 256. But the point is, there are more and more and more experts. Well, here, NVLink 72, we have 72 GPUs. And because of that, we could put 4 experts in one GPU. The most important thing you need to do for each GPU is to generate tokens, which is the amount of bandwidth that you have in HBM memory. We have one GPU generating thinking for 4 experts, versus here, because each one of the computers can only put 8 GPUs, we have to put 32 experts into one GPU. So this one GPU has to think for 32 experts, versus this system, each GPU only has to think for 4. And because of that, the speed difference is incredible. And this just came out. This is the benchmark done by Semi-Analysis. They do a really, really thorough job. And they benchmarked all of the GPUs that are benchmarkable. And it turns out it's not that many. If you look at the list of GPUs you can actually benchmark, is like 90% NVIDIA. Okay, so we're comparing ourselves to ourselves, but the second best GPU in the world is the H200 and runs all the workload. Grace Blackwell per GPU is 10 times the performance. Now, how do you get 10 times the performance when it's only twice the number of transistors? Well, the answer is extreme co-design. And by understanding the nature of the future of AI models, and we're thinking across that entire stack, we can create architectures for the future. This is a big deal. It says we can now respond a lot faster, but this is the even bigger deal. This next one, look at this. This says that the lowest cost tokens in the world are generated by Grace Blackwell NVLink 72, the most expensive computer. On the one hand, GB200 is the most expensive computer. On the other hand, its token generation capability is so great that it produces it at the lowest cost, because the tokens per second divided by the total cost of ownership of Grace Blackwell is so good. It is the lowest cost way to generate tokens. By doing so, delivering incredible performance, 10 times the performance, delivering 10 times lower cost, that virtuous cycle can continue. Which then brings me to this one. I just saw this literally yesterday. This is the CSP CapEx. People are asking me about CapEx these days, and this is a good way to look at it. In fact, the CapEx of the top 6 CSPs, and this one is Amazon, CoreWeave, Google, Meta, Microsoft, and Oracle. Okay, these CSPs together are going to invest this much in CapEx, and I would tell you the timing could be better. And the reason for that is now we have the Grace Blackwell NVLink 72 in all volume production, supply chain everywhere in the world is manufacturing it. So we can now deliver to all of them this new architecture so that the CapEx invests in instruments, computers that deliver the best TCO. Now, underneath this, there are two things that are going on. So when you look at this, it's actually fairly extraordinary. It's fairly extraordinary anyhow. But what's happening underneath is this. There are two platform shifts happening at the same time. One platform shift is going from general purpose computing to accelerated computing. Remember, accelerated computing, as I mentioned to you before, it does data processing, does image processing, computer graphics. It does computation of all kinds. It runs SQL, runs Spark, it runs, you ask it, you tell us what you need to have run, and I'm fairly certain we have an amazing library for you. You could be, a data center trying to make masks to manufacture semiconductors. We have a great library for you. And so underneath, irrespective of AI, the world is moving from general purpose computing to accelerated computing, irrespective of AI. And in fact, many of the CSPs already have services that have been here long ago before AI. Remember, they were invented in the era of machine learning, classical machine learning algorithms like XGBoost, algorithms like data frames that are used for recommender systems, collaborative filtering, content filtering. All of those technologies were created in the old days of general purpose computing. Even those algorithms, even those architectures are now better with accelerated computing. And so even without AI, the world's CSPs are going to invest into acceleration. NVIDIA's GPU is the only GPU that can do all of that plus AI. And ASIC might be able to do AI, but it can't do any of the others. NVIDIA can do all of that, which explains why it is so safe to just lean into NVIDIA's architecture. We have now reached our virtuous cycle, our inflection point. And this is quite extraordinary. I have many partners in the room, and all of you are part of our supply chain, and I know how hard you guys are working. I want to thank all of you, how hard you are working, and thank you very much. Now I'm going to show you why. This is what's going on in our company's business. We're seeing extraordinary growth for Grace Blackwell for all the reasons that I just mentioned. It's driven by two exponentials. We now have visibility. I think we're probably the first technology company in history to have visibility into $500 billion of cumulative Blackwell and early ramps of Rubin through 2026. And as you know, 2025 is not over yet, and 2026 hasn't started. This is how much business is on the books. $500 billion worth so far.
$500 billion.
Now this is, out of that, we've already shipped 6 million of the Blackwells in the first several quarters. I guess the first 4 quarters of production, 3.5 quarters of production. We still have 1 more quarter to go for 2025, and then we have 4 quarters. So the next 5 quarters, there's $500 billion, $500 billion. That's 5 times the growth rate of Hopper. That kind of tells you something. This is Hopper's entire life. This doesn't include China and Asia. So this is just the West. Okay, this is just or excluding China. So Hopper, in its entire life, 4 million GPUs. Blackwell, each one of the Blackwells has 2 GPUs in it in one large package. 20 million GPUs of Blackwells in the early parts of Rubin. Incredible growth. So I want to thank all of our supply chain partners, everybody. I know how hard you guys are working. I made a video to celebrate your work. Let's play it.
The age of AI has begun. Blackwell is its engine, an engineering marvel. In Arizona, it starts as a blank silicon wafer. Hundreds of chip processing and ultraviolet lithography steps build up each of the 200 billion transistors, layer by layer on a 12-inch wafer. In Indiana, HBM stacks will be assembled in parallel. HBM memory dies with 1,024 IOs
are fabricated using advanced EUV technology. Through silicon via is used in the backend to connect 12 stacks of HBM memory and base die to produce HBM. Meanwhile, the wafer is scribed into individual Blackwell die, tested and sorted, separating the good dies to move forward. The chip-on-wafer on substrate process attaches 32 Blackwell dies and 128 HBM stacks on a custom silicon interposer wafer. Metal interconnect traces are etched directly into it, connecting Blackwell GPUs and HBM stacks into each system and package unit, locking everything into place. Then the assembly is baked, molded, and cured, creating the GB300 Blackwell Ultra superchip. In Texas, robots will work around the clock to pick and place over 10,000 components onto the Grace Blackwell PCB. In California, Connect X8 SuperNICs for scale-out communications and Bluefield 3 DPUs for offloading and accelerating networking, storage, and security are carefully assembled into GB300 compute trays. NVLink is the breakthrough high-speed link that NVIDIA invented to connect multiple GPUs and scale up into a massive virtual GPU. The NVLink switch tray is constructed with NVLink switch chips, providing 14.4 terabytes per second of all-to-all bandwidth. NVLink spines form a custom blind-mated backplane with 5,000 copper cables connecting all 72 Blackwells, or 144 GPU dies, into one giant GPU, delivering 130 terabytes per second of all-to-all bandwidth, nearly the global internet's peak traffic. Skilled technicians assemble each of these parts into a rack-scale AI supercomputer. In total, 1.2 million components, 2 miles of copper cable, 130 trillion transistors, weighing nearly 2 tons. From silicon in Arizona and Indiana to systems in Texas, Blackwell and future NVIDIA AI factory generations will be built in America. Writing a new chapter in American history and industry. America's return to making and reindustrialization, reignited by the age of AI. The age of AI has begun. Made in America. Made for the world. We are manufacturing in America again. It is incredible. The first thing that President Trump asked me for is bring manufacturing back. Bring manufacturing back because it's necessary for national security. Bring manufacturing back because we want the jobs and we want that part of the economy. And 9 months later, we are now manufacturing in full production Blackwell in Arizona. Extreme Blackwell, GB200, Grace Blackwell, NVLink 72, Extreme co-design gives us 10x generationally. It's utterly incredible. Now, the part that's really incredible is this. This is the first AI supercomputer we made. This is in 2016 when I delivered it to a startup in San Francisco, which turned out to have been OpenAI. This was the computer. And in order to create that computer, we designed one chip. We designed one new chip. In order for us to do co-design now, look at all of the chips we have to do. This is what it takes. You're not going to take one chip and make a computer 10 times faster. That's not going to happen. The way to make computers 10 times faster so we can keep increasing the performance exponentially, we can keep driving costs down exponentially, is extreme co-design and working on all these different chips at the same time. We now have Ruben back home. This is Ruben. This is the Vera Ruben and Ruben. Ladies and gentlemen, Ruben. this is our third generation NVLink 72 rack scale computer. Third generation. GB200 was the first one. All of our partners around the world, I know how hard you guys worked. It was insanely hard. It was insanely hard to do. Second generation, so much smoother. And this generation, look at this, completely cableless. Completely cableless. And this is all back in the lab now. This is the next generation Rubin. While we're shipping GB300s, we're preparing Rubin to be in production, this time next year, maybe slightly earlier. And so every single year, we are going to come up with the most extreme co-design system so that we can keep driving up performance and keep driving down the token generation cost. Look at this. This is just an incredibly beautiful computer. Now, so this is amazing. This is 100 petaflops. I know it doesn't mean anything. 100 petaflops. But compared to the DGX1 I delivered to OpenAI 9 years ago, it's 100 times the performance right here versus 100 times of that supercomputer. 100 times, 100 of those, let's see, 100 of those would be like 25 of these racks, all replaced by this one thing. One.
And Radar Plex's new fucking processor there.
This is the compute tray.
Oh, God is good.
And this is, very Rubin super chip. Okay? And this is the compute tray.
Look at that shit.
Up right here. It's incredibly easy to install. Just flip these things open, shove it in. Even I could do it. Okay? And this is the Vera Rubin compute tray. If you decide you wanted to add a special processor, we've added another processor. It's called its context processor because the amount of context that we give AIs are larger and larger. We wanted to read a whole bunch of PDFs before it answered a question. We wanted to read a whole bunch of archive papers, watch a whole bunch of videos. Go learn all this before you answer a question for me. All of that context processing could be added. And so you see on the bottom,
context processing.
8 ConnectX-9
Vera
new
Rubin
Super
CPX
NICs.
compute tray.
You have CX.
1
You have
million token
CPXs,
content
8
accelerator.
of them. You have Bluefield 4, this new data processor, 2 Vera CPUs, and 4 Rubin packages, or 8 Rubin GPUs. All of that in this one node, completely cableless, 100% liquid cooled. And then this new processor, I won't talk too much about it today. I don't have enough time, but this is completely revolutionary. And the reason for that is because your AIs need to have more and more memory.
Yes.
You're interacting with it more. You wanted to remember our last conversation. Everything that you've learned on my behalf, please don't forget it when I come back next time.
4.
And so all of that memory is going to create this thing called KV caching. And that KV caching, retrieving it, you might have noticed, every time you go into your AIs these days, it takes longer and longer to refresh and retrieve all of the previous conversations. And the reason for that is that we need a revolutionary new processor, and that's called Bluefield 4. Next is the ConnectX switch, the NVLink switch, which is right here. Okay, this is the NVLink switch. This is what makes it possible for us to connect all of the computers together. And this switch is now several times the bandwidth of the entire world's
Rubin looks like
traffic.
the brain.
And so that spine is going to communicate and carry all of that data simultaneously to all of the GPUs. On top of that, this is the Spectrum X switch, and this Ethernet switch was designed so that all of the processors could talk to each other at the same time and not gum up the network. That's very technical. Okay, so these are these three combined, and then this is the quantum switch. This is for InfiniBand. This is Ethernet. We don't care what language you would like to use, whatever standard you like to use. We have great scaled out fabrics for you, whether it's InfiniBand or quantum or Spectrum. Ethernet, this one uses silicon photonics and it's completely co-packaged options. Basically, the laser comes right up to the silicon and connects it to our chips.
Laser to the silicon.
Okay, so this is the Spectrum X Ethernet. And so now let's talk about, thank you. This is what it looks like. This is a rack. This is 2.5. This is 2,000. This is 2 tons.
Yo, what the fuck
1.5
is
million
this?
parts.
Look at that
And
shit.
this spine right here carries the entire internet traffic in 1 second. Same speed, moves it across all of these different processors. 100% liquid cooled. All for the, fastest token generation rate in the world. Okay, so that's what a rack looks like. Now, that's one rack.
Unbelievable.
A gigawatt data center would have, call it, let's see, 16 racks would be 1,000, and then 500 of those. So whatever, 500 times 16. And so call it 9,000, 8,000 of these would be a 1 gigawatt data center. Okay? And so that's a future AI factory.
One gigawatt.
As you notice, NVIDIA started out by designing chips, and then we started to design systems, and we designed AI supercomputers. Now we're designing entire AI factories. Every single time we move out and we integrate more of the problem to solve, we come up with better solutions. We now build entire AI factories. This AI factory is what we're building